Hello, and welcome to another video lecture for Machine Design ME372. In this video lecture, we're going to continue our discussion of bolt design. In particular, we're going to first look at the static bolt design process. And this process is outlined in 5 steps, shown on this slide and the following slide. The first step is to determine the applied load per bolt. So you would take the total applied load and divide it by the number of bolts. Then we select a bolt material and we estimate a diameter for the bolt that will carry the applied load per bolt. This is where you need to be able to make good engineering judgment. You should have in the back of your mind a reference where you know that a certain size diameter rod will carry a certain load. The reference value that I use is what I remember from when I took a 250 type class. And we pulled a 1/4 inch rod till it yielded. And it took about 2,500 pounds to stretch that rod. And that was a 1/4 inch rod. So that's kind of the reference point that I use when I am selecting bolts to carry certain loads. I know that a 1/4 inch rod will carry on the order of 2,500 to 3,000 pounds. And then if that's made of mild steel. And then I can get an idea of where I need to be to estimate the diameter of the bolt based on the actual applied load that I have for the situation I'm looking at. So you need to get your reference point and remember a reference that you can use throughout your career. The next steps for a static bolt design are a little bit different and a little confusing at first. What we want to do is we want to compute the preload using this range right here, where we have 0.75 FP to 0.9 FP. So we want our preload to be between 90% of FP and 75% FP. Now, if we want to compute closer to this 75% FP for bolts that will be put in and taken out and put in and taken out. If it's more of a permanent connection, then you can come closer to the 90% FP. Now FP is the proof load, and it's computed by taking the tensile stress area times the proof strength, where the proof strength comes from a lookup table. And this is given in tables 8, 9, 10, and 11. So chapter 8, tables 9, 10, and 11, you can look up values for the proof strength. The proof load is the maximum force that a bolt can withstand without acquiring a permanent set. So without any plastic deformation, the maximum load that can be applied is the proof load. An approximation to the proof strength is given by 85% of the yield strength. So you remember when we deal with yield strength, we actually have a 0.2% plastic deformation. And so we have to reduce the strength value to not have any plastic deformation. And the reduction is to take about 85% of the yield strength, or to look up the proof strength in a table. So the idea is we select our material and we look up the proof strength. And then we can compute 90 and 75% of that, and we want our preload to be in that range. And we compute the preload using this expression here for a static bolt design, where we have preload is equal to tensile stress area times the proof strength minus eta L CP. Now AT is a lookup value, that's easy. SP is a lookup value, that's easy. A to L is the load factor, it's the safety factor. And there are tables and expressions for all of those values. C here is the challenge to compute. C is called the joint stiffness, and it is computed by taking the stiffness of the bolt divided by the sum of the bolt stiffness and the member stiffness. So C is KB over KB plus KM. So C is a challenge to compute because we have to go get the bolt stiffness and the member stiffness. P is the applied load per bolt. Then the last step is to check for bolt spacing. And to maintain uniformity, bolts should not be spaced more than 6 diameters apart if you're looking to clamp on a bulkhead, for example. Your bolts should be closer than 6 diameters apart. To maintain wrench clearance, bolts should be spaced at least 3 diameters apart. And this one, there's some fluctuation and leniency in this one for sure, because we have socket wrenches and stuff that do not require at least 3 diameters apart. Both of these, and especially this 3 diameters apart, are very loose design rules, and other constraints typically govern the design on the bolt spacing. So what happens is the process then is we determine the load per bolt, we pick a diameter, we come and we compute Fi, then we come back and see if Fi falls in this range. If Fi is outside the range because it's too big, then we've selected too large of a bolt and we need to go back and select a smaller bolt diameter and go through this entire process again. If we're down here below the 75% FP, then we've picked too small of a bolt and we need to come back and pick a larger bolt and go back through and compute Fi. You will be asked to go through this static bolt design in your homework and on an exam. So you will not have these notes open to you to define the process, but you will certainly have access to the equations used to compute the needed terms in the process. So make sure you can do a static bolt design. For fatigue, it's a very similar approach. The only thing that is different is now that Fi is based on a different equation. And here's the equation for Fi in a fatigue bolt design process. We have AT, but instead of the proof strength, we now use the ultimate strength. Here's our A to L, here's our joint stiffness again, here's our load per bolt P, and then we have SUT over SE, where SE is the modified endurance factor or the fatigue limit. And for bolted joints, this typically comes from a lookup table. Later on, when we talk about fatigue this semester, we will actually spend a significant amount of time computing modified endurance limits or endurance factors for different scenarios. But in terms of bolts and bolt design, we can often look up the endurance limit for the bolt design. And we can find that in many manuals and machine design textbooks and handbooks that talk about bolt design. They will have a table of the modified endurance values. So that's the process, that's the outline. We will now look at an example of a static bolt design and actually go through and look up all the equations. Let's go through a detailed example of a static bolt design. In this example, we have a cylinder head shown here by this crosshatch top material. And we have that bulkhead, or this cylinder head, bolted to this cylinder shown down here. We can see that there is a pressure inside of here that can be applied. Now, in terms of dimensions and bolts, all of that information is given here. We know that the dimension A is 80 millimeters. B here from bolt to bolt is 200. C from outside to outside is 300. W from the gasket to the gasket is 100. D here, the thickness of the top plate is 20, and E here, the thickness of the cylinder head part is 25. We know the internal pressure is static at a magnitude of 6 megapascals. And we're to use metric grade 8.8 bolts with a safety factor of 3. And we need to size the bolts for this application. One of the things that we need to consider first is the force in the bolts. And we need to determine that force by understanding the pressure loading from the cylinder cavity. And looking at this, we know that A will have an internal, this dimension A, there's an internal pressure here that's pushing out on this top cap and the cylinder head. And when we look at the area over which the pressure's distributed, there are a couple different options for us. Certainly I could see where we would only consider the area A, or the area computed from this dimension A. However, I also see that we might have pressure that comes out to the gasket. And if this pressure leaks out to the gasket, I could see that we would actually have a pressure acting over the area computed by using W. If we have the pressure go past the gasket, that's typically a poor design, and we would have a leaky cylinder head. In this example, we'll go ahead and use the dimension W to compute the area over which the pressure acts, which will allow us to compute the force per bolt. So let's follow our basic approach that we talked about just previously. So we'll follow the steps just outlined. We'll compute the required preload range based on the bolt material properties using this expression here. We'll need to select or assume a bolt diameter and solve for Fi based on equation 829, page 440, which is also given below down here. And then if our assumed bolt diameter fits the range, we're okay. If not, we'll try another D. So that's the basic process that we're going to follow. To determine the load per bolt, we're going to take the total load on the cylinder head due to the internal pressure. And we know the pressure is 6 megapascals, and we're going to use W here as our dimension over which that acts. So to find the total force, we take the pressure times the area, and that'll give us the total force on the cylinder head. So the pressure is 6e to the 6th, the area would be pi d squared over 4, where our d is the W dimension of 100 millimeters, and we'll put that in units of meters, and we'll compute 47,000 newtons for the total force on the bulkhead. Now we're given that we have 10 bolts, so we're going to use 10 bolts on this cylinder head, and so the load per bolt is the 47,000 divided by 10 gives us 4,000 newtons per bolt. Now we need to select a bolt diameter and material based on engineering judgment. And based on engineering judgment, we'll assume a bolt diameter of D equal to 16 millimeters. And the material properties are as given below, where for a 16 millimeter diameter bolt, AT is 157 millimeters squared, and then we can get SP, SUT, and SY. Now, here's an aside note on metric classification. When the metric bolts are specified, they have a grade of some number, decimal point, and then some number. This first number is equal to 0.01 times the SUT in megapascals. The second number here is decimal point second number, which would be equal to the ratio of SY over SUT. So if you know we have a metric grade 8.8 bolt, that means we can come here and take the 8, divide it by 0.01 and get 800, and that would mean we have 800 megapascals for our SUT. And you can see from the table we looked up 830, which is very close. Then we would take the, if we have an 8.8, would take the 0.8 and set that equal to the SY over the SUT. And if our SUT is 800 and we multiply that by 0.8, we get 640, which is very close to the 660 SY that we're using here. So this is a great thing to remember, that you can actually compute the ultimate strength and the yield strength directly from the grade of the bolt, where you can't do that with the English classification. So we're going to compute the required preload now, and to do that we need to get the proof load, and the proof load is given by the tensile stress area times SP, the proof strength. We know the AT because we looked it up, and we can get the proof load by looking it up from table 8, 9, 10, and 11, or we could take 85% of 660 and also get an approximate value for the proof load or the proof strength. So here we'll use 600 as the proof strength, and we compute our proof load as 94,200. So coming and plugging that into our range, we want our bolt range to be between 70,000 and 85,000. If the calculated preload falls in this range, it's a good design, it's an adequate design. If the calculated preload is too high, the selected bolt is too big, and we need to pick a smaller bolt. If the calculated preload is too low, we need to pick a stronger or a bigger bolt. So now we come down to compute the preload, and to compute the preload we use this expression here. We know AT and we know SP. We know our safety factor was given as eta L equals 3, and we know the load per bolt is 4,712. What we need to do is compute the joint stiffness C. And to do that, we need to compute the bolt stiffness and the member stiffness. So, as a quick approach to look at the K-bolt, we can neglect the threads and assume that all of the material in the grip is unthreaded shaft or an unthreaded bolt. And doing that, we get AE over L for K-bolt, where the A is based on the 16 millimeter diameter bolt that we assumed we have. E was given and the length of the grip is 0.045. When we do that, we get approximately 925 meganewtons per meter for KB. Now let's be careful about how we compute KB and do the detailed approach. Here we have L, and the length will be the 20 for the top cap, 25 for the thickness of the cylinder. Then we have the nut, and then we're going to use 2 threads past the nut. So we're going to have 20 plus 25 plus 14.8. Now in this 14.8 comes from table A31 in your appendix. It's more on page 1074 or so. Then we have the makeup, and the makeup replaces the 2 threads. If we wanted to go 2 threads, what we would do is simply add 2 times the pitch here. And for this particular bowl, our pitch is 2 millimeters, so 2 times 2 would be 4. But when I add the 20, the 25, and the 14.8, I get 59.8 for a length. And that's not a standard length, so I round up to the next standard length. And on table A17, we get that standard length of 60. And so the standard length of the bolt that I will use is 60 millimeters. Now I need to go get the threaded length of the bolt, and to do that I use this equation given as equation 814. So I can compute the threaded length of the bolt. Now I can get the little ld, the length of the unthreaded portion of the bolt that's in the grip, by taking the 60 minus the 38 to get 22. Then I can get the threaded portion of the bolt in the grip, which is 45 minus the 22 gives me 23. So I now have all the terms I need to compute K bolt. So I compute AD, which is the area of the unthreaded portion of the shaft. I use just the diameter of the bolt, so I'll use the 0.016. AT is a lookup value from the table, and then I know the modulus of elasticity. Coming down here, I have my AD again times the threaded length, which is this 23, and then I have my AT times LD, which is the unthreaded length, which is the 22. And computing this KB, I get 808 meganewtons per meter. So when we compare the quick approach of 925 to the more detailed approach of 808, we can see that there is a significant difference. We also see that by assuming the bolt is completely unthreaded in the entire grip, we overestimate the stiffness of the bolt. So computing this KB will always be an upper bound on computing the KB when we consider both the threaded and the unthreaded portions. Now we need to look at computing Km, the member stiffness. To do that, we come over and we draw a picture of our cones. And so this distance here is the grip. This first material we know is 20 millimeters thick, and the second material representing the cap on the actual cylinder was 25 millimeters thick. And so we find the geometric center, and the geometric center will occur at 22.5, because that is half of the overall 45 millimeter length or grip length. So we know that we'll have a top cone, and then we change into the different material. for just a little bit before we hit the peak of the cone at the halfway mark. So here we'll have 20 millimeters of the entire top material. Then we have 2.5 millimeters of the bottom cylinder material. And then our final third cone will be all the bottom material, or the material of the cylinder. So I need to come and compute K for each one of these springs, or each one of these cones. To do that, I'm going to use this basic equation right here. For the top cone, we know that big D is equal to 1.5 little d. So writing this all out, I have the 0.577 pi, E is 207 e to the 9th, and D is 16 millimeters. Then I have the ln of 1.15 times t, and the thickness of this cone here, the first cone, is 20 millimeters, so 0.02, plus big D, and big D for the first cone is 1.5 times little d, which is 0.016. And then I have minus little d and the rest of the terms, and I can compute that to be 6.6 e to the 9th. Now I look at my second cone, and the second cone is given by this small little cone in here, identified by the circled number 2. And in order to compute K2, I have to compute big D for this cone. And again, big D is the smallest side of the cone. So big D is this length from here to here. And to compute that number, we know that this angle here is 30 degrees. And we know that the tangent of 30 is equal to x over 20. And so solving for x, which is this distance here, I get 11.5. So my big D2 will be the 1.5 times the little d up here to get this distance, the distance of my first cone. So this should be 1.5 little d, or the 16, plus 2 times x, where x is this distance, and I have an x on this side and an x on this side, and that's why I have the 2. So big D2 is 1.5 times 16 to get this distance, and then 2 times 11.547 to get this distance and this distance, and I add them up and get 47. The thickness of this cone is only 2.5. So here again I have the 0.577 pi ED. Here I have the 1.15 times the thickness of this cone, which is 0.0025 meters. Then I have my big D2, which is 0.047 meters, and then little d of my bolt, and that's 0.016. Now when I go to compute K3, K3 now is bounded by this side. The smallest edge of this cone is this bottom side, and this is the side that's next to the nut. So again, this is 1.5 little d, and the thickness of this portion is 22.5. So here for K3, I have 1.15 times the thickness, which is 22.5 millimeters, then 1.5 little d again, and then 0.016. So now I have K1, K2, and K3, and to get K total, I sum up the inverses of these Ks and invert it, and I get K of the material. And I get 3.178 e to the 9th newtons per meter. And note that this is much larger than KB. For KB, we had 808 here we have, this was 808 e to the 6th. Here we have 3.1 e to the 9th. So as expected, our K material is much bigger than K bolt. And we can use that as kind of a check to make us feel good about our numbers that we have computed. So now I can compute the joint stiffness C by KB over KB plus KM, and I get 0.016. So I now come and compute the preload. I have all the terms and I can compute the preload, and I get 91.9. And 91.938 is greater than the upper end of the desired preload of 84,000. So back a couple pages, we computed the desired preload upper bound to be 84,780. And we just computed 91,000 for our preload. And so we have selected too big of a bolt. And what we want to do is go back and pick a smaller diameter bolt and redo all the calculations. So I've done that here. If you assume D is equal to 10 millimeters, then you can come through the entire process again. You'll note that you have to do all of the L's again. You have to do KB. We have to do KM. And so we'll have to do K1, K2, and K3 and get all of our Ks. And then we have to come and compute our preload again. This time, when we computed the preload, we have 31,577 newtons. And the new range for the preload that we computed back here was 31,320 for an upper bound. So we can see that we are just barely outside the upper bound limit. And if we wanted to make sure that these bolts would carry the load, we would use this 10 millimeter diameter bolt. So it's important to note that when you pick a new bolt diameter, you have to do the entire process again, including computing a new preload range. And so I had to come and get the proof load, get the proof strength, get the range on my preload, go get all of the L's, KB, KM, and compute all of these numbers, and then compare the FI to the new preload range. So in this design, I would go ahead and use the 10 millimeter bolt diameter because the 31,577 is close enough to the upper limit here of 31,320. It is a stronger bolt than may be needed, but it is close enough to the range that I would use that. If I wanted to be very careful and do a careful design, minimizing the bolt diameter, I would probably come back now and pick D as an 8 millimeter diameter bolt, redo all the analysis, and we would find that we fall in the range a little better. We can then compute the torque, and the torque to which we need to tighten these is given by KFID, and we get K from table 815. And we know the preload FI, and we know the diameter of the bolt, so we can get the torque spec to which we want to tighten these bolts. And we can get that to be 63.15 newtons per meter. So this expression here, torque is equal to KFID, is an important equation. Note that this K is a different K than the K's up here for the member and bolt stiffness. And we can look that value up from table A15. Then we can check our bolt spacing. We know that we want our bolt spacing to be between 3 and 6 diameters. Here we end up with a bolt spacing of 6.28, which is a little bit high, but as we discussed. So I will expect you to be able to go through this static bolt design process on homework and on an exam. If you have questions about this, we can certainly review it in our in-class review sessions. Let's look at safety factors. There are several different safety factors in bolts. We have the axial stress is computed by force in the bolt divided by AT, and this can also be expressed as CP plus FI over AT, where C is the joint stiffness, P is the load per bolt, FI is the preload, and AT is the tensile stress area. We have the yielding factor of safety given by SP over sigma B. Then we have the load factor, which is given by A to L equal to SPAT minus FI over CP. This one here is commonly used. This is the general safety factor that's used in the expressions to compute FI. Then we have the joint separation factor, which is A to naught, given by Fi over P times 1 minus C. So I won't expect you to memorize these expressions, but you certainly need to know which one we are talking about when we use them in equations. And for example, if I asked you to compute the joint separation factor, you would need to come and look up this equation and compute this quantity. In fatigue, we look at alternating and mean stresses. And so if we have an external load on a bolt that fluctuates between a minimum load and a maximum load, we can compute an alternating load and a mean load. So the force on the bolt minimum would be C times P min plus Fi, where P min is the minimum applied load. And then force on the bolt max, the maximum force in the bolt would be C times P max, where P would be the maximum externally applied load plus Fi. And you can see here how this joint stiffness, which is usually significantly less than 1, reduces the overall P that is applied to the force in the bolt. Now, to come and compute the alternating stresses, we have several forms of the equation that we can use to compute those alternating stresses. To compute the mean stresses, we also have several forms of the equation that we can use. So we need to make sure that we can compute the alternating stresses and the mean stresses in a bolt problem where the load is alternating between a minimum and a maximum value. What we do then to look at the failure of these types of systems is we plot the mean stress or the steady stress down here on the x-axis, and we plot the alternating stress on the vertical axis. And we mark off limits on this, where we mark off the SUT on the mean stress and SE on the alternating stress. So if I had a bolt that did not see any alternating stress, the maximum load that could be applied to that bolt would be the SUT. And so you see that failure is based on the ultimate strength using this model. If I had a bolt that saw completely reversed loading, so the mean stress was equal to 0, which means it went in tension and then compression and then tension and compression. And if I had a completely alternating stress, the maximum value would be SE, which is called the endurance limit. And this endurance limit represents the maximum stress that can be applied to the bolt without the bolt failing in fatigue. Then we come over here and we can look at our particular problem, and we can look at our Fi over our AT, and we can plot what we call a load line. And we'll look at this in more detail. Table 817 in your textbook gives you a list of endurance limit values for grade and class bolts. So here we have an SAE grade 8 bolt with a size range of 1/4 to 1.5 inches, and our endurance limit is 23.2 kpsi. And then for ISO class bolts, we can look up the size range and the endurance limit. And this is based on repeatedly applied axial loading, and this is a fully corrected, including a stress concentration factor as a strength reducer. So this endurance limit here is fully corrected. Now, if you can't find your particular bolt or class in this table, what do? Well, you can extrapolate to some degree using these values. And for a homework problem, that may be what I would do. In a design situation, I would probably go find a more in-depth, more detailed table that I could look up the endurance limit for the particular bolt that I have in my design. And you might be able to find some of this online, where you can look up the endurance strengths for different grade and class bolts. The equation of the load line shown here is given by SA is equal to the alternating stress over the mean stress minus the preload stress times the quantity SM minus SI, where the SM and the SI are the values that give the equation a value of 1. So these are the alternating strength and the mean strength. The equation of the Goodman line, the equation of this line right here, is given by this expression right here. And this represents the failure line. If we have an alternating and a mean stress that put us inside of this envelope or below this line, we have a safe design. If we have a mean and an alternating stress that put us outside of this line, out in this region here, then our bolt will not last in fatigue and we will have a failure. For fatigue factors of safety, we have NF, which is the fatigue factor of safety based on the Goodman line and the constant preload line. And we would have NF as SA over sigma A. Other failure curves can be used, and following the same approach, we get NF is equal to this expression here. For the repeated load case, we can see that our alternating stress can be expressed as this equation, and with a constant preload line, we get our mean stress as expressed here, and our load line has a slope of unity for the repeated load case, and we can get this expression here. Here are the equations for different failure curves. The Goodman is the one that we will generally use and is the default equation. The Gerber simply squares this component. So the Goodman and the Gerber line are exactly the same, except Gerber squares this component. And the ASME elliptic is exactly the same as the Goodman, except it squares both the first term and the second term, and it replaces the SUT with SP. So these three failure theories are similar in that the equations look very similar, and there's only a difference in the terms that are squared, and then the SUT becomes SP when we look at the ASME elliptic curve. In the following pages of the note packet, there are several equations that are listed. And I would encourage you to read through your textbook. These equations come directly from your textbook. And read through your textbook in this section and make sure that you understand where these equations are coming from and that you can use them. We will now look at solving an example problem. In this example problem, we have a welded steel bracket as shown down here, and it's bolted underneath a structural steel ceiling beam to support a fluctuating tensile load imposed on it by a pin and a yoke, so a load applied down here. The bolts are 1/2" coarse thread SAE grade 5, tightened to the recommended preload. The stiffnesses have already been computed and are KB and KM. Assuming the bolts rather than the welds govern the strength of this design, determine the safe repeated load P that can be imposed on this assembly using the modified Goodman criterion and a fatigue design factor of 2. Compute the load factors. So to do that, we need to realize that our load is a load that is applied and released. And so it's not a completely reversed load, but it goes from 0 to a P max. So the solution process for this is we will use the modified Goodman expression for our failure, and we'll solve this expression for SA, and then we'll compute the alternating force and apply the safety factor. So looking up the bolt in the tables, we can get AT, SP, SUT, and SE from these tables here. Now I can come and compute my preload, and I'll compute the preload as 75% of my proof load, and I compute FI here. This is equation 8, 31, and 32. Then I can come and compute SA, which is the alternating strength. So I can compute my SA and get 7.55. Then using my safety factor equation, I have A to F is SA over sigma A, and I can solve for sigma A from this expression because I just solved for SA and I know my safety factor is 2. So I know the maximum alternating load on this system could be 3.775 kpsi. That's the maximum alternating stress in the bolt. So now I can come and use this expression here for the 0 to P max case. And this expression sigma A comes from back here on equation 839, page 279 in the note packet, where we are alternating between 0 and a P max. And now I can take this expression and solve for the P. So doing that, I can come down here and my K's were given, so I can compute C, and then I can solve for, use this equation, and I know that this equals 3.775, and I can solve this expression for PA and get 4,000 pounds, 4,539.6 pounds. And this is the alternating load that could be applied to the bolted system and not have a failure. And now I can come and compute my load factors and my joint separation factor. So this is a good example to show you how to use safety factors and the different loads to compute the maximum load that could be applied to a bolted joint system in a fatigue type application. As a bolt preload summary, we have for static loading, A to L is given by this equation. For fatigue, we have fatigue loading given as the alternating and the mean stresses. The important thing here to remember is that in fatigue loading, a high preload really improves the design. So large FI and fatigue loading greatly reduces the alternating loads and improves the life of the bolted joint. If you have a fatigue situation and a low preload, then you can get large alternating stresses on the bolt and your system will fail. In a static scenario, the large preload is not as significant or as important as it is in a fatigue loading situation.